Hello and welcome to Lecture 3 of Embedded Systems, in which I shall try to cover the general purpose digital input-output operations that can be performed with the help of microcontroller cortex-m, and I shall also discuss how to configure the I/O ports for different purposes, obviously with the help of an example to illustrate how to interface a switch and LED, the basic components, basic peripherals that can be interfaced with the Cortex-M4 microcontroller. As already mentioned, the agenda items include the discussion of I/O ports, that is how to configure these I/O ports and how to send and receive data to and from the I/O ports, and how to interface some very basic components such as a switch or an LED to the microcontroller. Now, if you can recall, we discussed in the very first lecture that our microcontroller can have several input-output ports. So here in this case, we have port A through port AF, so 6 different input-output ports. And there can be at most 8 pins on any port. Some of them may have less than 8 pins, like in case of port F. Nevertheless, in case of all the input-output ports, there are some pins that can have alternate functions. So you can see that in case of port A, it can be used either as a general purpose input-output operation, or it can be used to implement such as some serial communication protocols, such as UART protocol, or such as SSI interface protocol, and in some cases you can also implement I2C. That's because these modules are connected internally to this port. So remember, we can use the ports on the microcontroller either for the general purpose input-output operation or some alternate functions which are specific. And some of these will be discussed in our future lectures as well. All right, so I/O ports in the microcontroller are memory mapped. What do we mean by that? Well, it means that the data of the I/O port resides in the memory, or some portion of the memory, that's RAM. So you could, if you have to access data of the I/O port, then you have to access the memory or a special portion of the memory. The other vital component of a memory mapped I/O is that the configuration registers, that is the registers that we are going to write for the purpose of configuring an I/O port, those registers also live inside the memory. So in both cases, whether we wish to configure the I/O port for some, or we wish to program the I/O port for some specific application or some specific purpose, that information or those configuration bits need to be written into some memory location. And again, if we are operating the ports for the input-output task, again we have to access certain portion of the memory. In the discussion to follow, we are going to refer to some port, call it port X, and that can be port A through port F. We may need to read following configuration registers. So this discussion of the configuration register is important because a versatile microcontroller offers a lot of functionalities. So it is important to learn how to configure the I/O ports for the specific task that we are interested in. So let's now look at what are those configuration registers and how to set to reset the specific bits as required by the specific application. All right, so we have several registers for configuring the I/O ports. This is by no means a complete list, but the list that we would be mostly interested in our programs. The first one is the clock register. In order to use the ports for the general input-output task and for other tasks, it is important to enable its clock. Because the data that needs to be read in and data that needs to be outputted is synchronized with the clock. The other register is the analog mode select register that tells us if we wish to use a given I/O port or its pins for the analog input-output purposes. And that flexibility is there because we have an ADC inside the microcontroller, and that ADC is connected to the port with the help of buses. So essentially, this register tells us we use this register to connect the ADC with the I/O ports. That is how we enable or disable the connection. So is the connection there, or is the connection not there, is determined by the contents of this register, the analog mode select. All right, the next one is the direction register. Direction register is used to configure the port or its pins either as the input port or the output port. So here is the direction register. The bits of this register can be set so that we can enable some pins as the input or some of the pins on the port as the output. So it's basically configuring the port or some of its pin for either the input that is we wish to read data from the port, or we wish to output data at the port. The digital enable register. This register is used to configure port as, or some of its pins as the digital port or its pins. That is the data that is inputted from the port, or the data that is outputted to the port is taken as a digital data, logic high or logic low. Now note that if we disable the bits in the analog mode select register, that does not automatically means that the corresponding pins are to be used for the digital input output operation. So you have to separately set this digital enable register, and you have to separately set the analog mode select register. So those need to be set, or those registers need to be written separately. The next one is the alternate function, should I say the special function enable register. Like we said in the beginning, that each port, well, some of the port pins can be used for implementing special functions such as serial communication protocols, the I2C, SSI, and the UART. Therefore, if we wish to enable the port or some of its pin, and we want to configure them to perform those special functions, special tasks, then we have to enable, you have to set bits in the register. That's the special function enable register. So this we would be interested in writing to this register if we want to perform a special function at our ports. Then comes the special function specify register. So this seems to be linked with the one that we have just discussed, the enable. So in case you enable some of the bits of this alternate or special function register, then you'd have to specify, because there can be multiple special function registers. There can be multiple. There can be multiple functions. So which alternate or which special function that we wish to implement is described by the contents of the special function specify register. So multiple special functions. Okay. Um, this register, once again, special function specify register, selects the special selects one of the special function that we wish to perform on the port. And like we said before, the port X can refer to port A, B, C through port F. Now each IO port configuration register is a 32-bit long. In most cases, however, we would be interested only in the least significant 8 bits, often corresponding to either the port number or the 8 pins, because we said that there can be at most 8 pins on the port. Therefore, the lower 8 bits would be most crucial in many cases. And however, there will be certain instances where the upper 24 bits will also be written too. For example, in case of the clock register, we use the lower 8 bits to enable the clock on the corresponding port. For instance, if we are interested in enabling the clock on port D, then we are going to set the 4th bit of this register to 1. Assuming that we wish to disable clock on the remaining ports, then the only bit that we are interested in setting is the 4th bit. So starting from the least significant bit, that is the 0th bit. So that's the 0th bit. And so this one is going to be the 4th bit. And in this case, the 0th bit corresponds to port A. The first bit, or bit number 1, corresponds to port B, and bit number 2 corresponds to port C, and that's where bit 3 corresponds to port D. And in this case, we are not interested in the upper 24 bits because we are not going to have 24 ports. In fact, we are limited by 6 ports only on our microcontroller. Another example is that of the direction register that we write to for setting the ports or some of its pin, either for inputting the data or for outputting the data. For example, if we wish to set pin number 7 on port A, and remember the pin indices start from 0, not 1. So pin number 7 means the 8th pin of port A. If we wish to set pin number 7 on port A as the output pin, that's where we wish to output data, then we are going to set bit number 7. Again, the bit indices start from 0 as described earlier. So bit number 7 is the 8th bit, this guy. 8th bit of the direction register will be set equal to 1. And in this example, we are setting the first 7 bits, that is bit number 0 through bit number 6. They are set to 0, which means that we are setting the first 7 bits as the input. So the first 7 bits are telling microcontroller to use port A, first 7 pins as the input pins, and the 8th pin to be used as the output pin. I beg your pardon. So bit 0 corresponds to pin number 0, bit 1 corresponds to pin number 1, and so on. That is on port A. So there is one-to-one correspondence between the bits of the direction register with the pins of port A, and then that is often the case in several configuration registers. Under special circumstances, when we wish to access certain port pins, those ports need to be unlocked first. for instance, pin number 7 on port D and pin number 0 on port F in a microcontroller that we are going to use in our lab. When you wish to access these pins, then some unlocking is required, and for that purpose we have two registers that need to be written to with some special values. Check those out in the program 2.6 of the textbook, second textbook that is. In case of the special function specify register, one may need to write all 32 bits, and that's because there are or there can be at most 8 pins on any port, and we need 4 bits to specify the special or the alternate function. Therefore 4 times 8 is 32, and this is how this register 32 bits, all 32 bits of this register may be simultaneously required to be updated. And there's a table 2.7 of the second textbook, and there's a corresponding table in the first textbook to look at how you wish to update the contents of the special function specify register based upon the function that we wish to implement on the port. And finally, we have the port data register. If we want to read data into the microcontroller from the port X, then we are going to read this register. Conversely, if we want to write or if we wish to output data to the port, write this register. That will send data to the port X. We are now going to look at an example of reading data from the port. That is when we want to interface a switch to the microcontroller, and we want to know if the switch has been pressed or not, and that can be done in 2 ways using the negative logic. In this case, the switch is one end of the switch is connected to the ground, the other end is connected to the microcontroller, and it is common to the resistance whose other end is connected to the positive supply voltage, that is 3.3 volts. So in this case, if the switch is pressed, then naturally the microcontroller pin will be pulled down and will have 0 volts. That's so in that case, the switch press corresponds to 0 volts, that is logic low. In the other case, when the switch is connected, when the switch has one of its ends connected to the microcontroller pin, port pin, but the other end can be connected to the high voltage, that is 3.3 volts, and the end that is connected to the microcontroller pin is connected to the resistance through which the microcontroller pin is grounded. So in this case, if the switch is released, the switch is not pressed, then quite naturally the pin so the pin voltage will read 0 because there is no current that is going through the resistance. So remember, when the switch is released, in this case, the current through the resistance is essentially 0. There is no voltage drop. Therefore, the resistance is essentially short-circuited. That is when the switch is released. Switch is here. It's not pressed. Therefore, the switch is released. There is 0 volts on the pin, and when the switch is pressed, that is when the switch is connected to the high voltage, 3.3 volts. Then the pin of the microcontroller is pulled high, and it will read high voltage in this case. So the switch press corresponds to the high voltage in case of the positive logic, and the switch pressed corresponds to low voltage in case of negative logic. And this can be further illustrated with the help of the status of the switch. And again, you can use the negative logic based operation, or you can use the positive logic based operation. And in each case, uh, we have the switch on and off, or the switch press or release, uh, corresponding to different voltage levels, but those are read as a digital voltages: 0, high voltage, in this case 3.3, and the high voltage 0 volt, that is low voltage. So this is again just a recap of what we have already described in the previous slide. I'm now going to describe an assembly code in the form of a routine that initializes and prepares port A, pin number 5, to be configured as an input digital pin. The label of the routine is port init, and it ends with an instruction that returns the control back to the caller. That is the routine which actually called this port init routine. The first instruction loads a number into register R1. This number is an address of the clock register. This is the clock register. When you put an equals to sign, it means that we are going to put the address of this clock register relative to the program counter. So the first instruction uses the program counter relative addressing mode, or the PC relative addressing mode, to put an address of the clock register into register R1. Then, once the address has been loaded into register R1, next instruction utilizes that address and invokes index addressing mode to access the data of the clock register. Essentially, this instruction says that go to the address specified by the contents of register R1, fetch the data available at the address, which is the data of the clock register, and put it, and actually, to be technically correct, copy that data into register R0. So now we have read in the value of the clock register into register R0. Because we wish to use port A, and that's where the switch is connected. Remember that we are going to connect switch at pin number 5 of port A, pin number 5. So we have to enable the clock on port A. The least significant bit of the clock register corresponds to port A. So we are just going to set that bit to 1 using the OR instruction. So when we set the 0th bit of R0 equals to 1, we enable the clock on port A. But that's not done unless we write back the updated value, because the value has just been updated inside the register, not on the clock register yet. The value has not been updated to the clock register yet. So we need to write back the updated value. We invoke the store instruction, write back the updated value of R0, in which the least significant bit has been set equal to 1. That is going to store the value, and that is going to update the contents of the clock register. Once the contents of the clock register are updated, the least significant bit, whose least significant bit is 1, that enables clock on port A. Okay. After enabling the clock, the next task is to set the direction of the port pin. In this case, we are going to load the address of port A direction register, and we are going to fetch data of this register, fetch the contents of this register into R0. So R0 contains a copy of the data of the direction register, and in this case we wish to use the pin number 5 of port A, which means the bit number 5 of port A, needs to be configured as an input pin. Therefore, we are going to invoke another instruction, BIC, that is used to clear uh, the fifth bit, that is going to reset the fifth bit of the register R0. So once the fifth bit that corresponds to the pin number 5 of port A, the fifth bit of R0 corresponds to pin number 5 of port A. That bit has been reset, and we need to write it back using the store instruction. So the direction of the pin number 5 of port A has been set such that it is now going to act as an input port by setting the port direction register. Once the direction has been set and the clock has been enabled, then the final step is to enable the digital functionality of the port. For this case, the register is the digital enable register. We'll repeat the same steps. We're going to use the PC relative addressing mode using this equals to sign. We are going to load the address of that register into R1. Then we use indexing addressing to read in the contents of the digital enable register, copy those contents into register R0, and once the data is in the register, we are going to use the OR instruction. And this time we are using OR instruction because we want to put this really is set. There's a mistake here. This is actually set. We're going to set the fifth bit of register R0 equals to 1. And when we do that, this corresponds to making pin 5 of port A as digital port, and we're going to, and that is not complete until we actually update the contents of this digital enable register. So write back the updated register contents R0. So remember, data is still in R0. We need to write it back to the digital enable register. So store the updated R0 such that the digital enable register write back its value and update the digital enable register. And finally, the last instruction is BXLR, meaning that we're going to give the control back to the caller. So whichever routine called the so this actually is port initiation. So whichever routine called the port initiation routine, we are going to go back and execute therefrom, execute the remaining program therefrom. The two instructions NOP are the no operation instruction, meaning we are telling microcontroller do nothing. Those are inserted once the clock was enabled. That's because we want to wait for some period of time before the clocks become stable. So you may need to insert multiple no operation instruction to ensure that the clock is stable once it is enabled. Insert some wait cycles to make sure that the clock is stable and then proceed therefrom. We're now going to write a routine to interface switch to the pin number 5 of port A. The label is switch input 1. This is one of the routines to read in the value of the switch connected to pin 5 port A. The first command loads the address of the data register, port A data register, into R1. And again, we are going to index R1 to read in the contents of the port A data that goes into R0. And note that in this case, we are reading the full port A data, including the data on all the pins, not just pin number 5. The whole port data is read into register R0. And then we're going to take an AND with hex 20. which really means that we are going to uh, uh, retain the fifth bit of the register. We're going to retain only the fifth bit of register R0, and we are going to reset all other bits essentially to 0. So reset really means that we're going to set them equals to 0. And in the case where the switch is pressed, then assuming we are working with the positive logic, we are going to get 1 into R0. And that's because the port A, bit number 5, will be connected to the high voltage. Hence, R0 will be equals, the bit number 5 of R0 will be equals to 1. All of the bits are 0. So R0 will read hex to 0. And if the switch is not pressed, assuming the positive logic once again, then bit number 5 will be equals to 0. And then once we are finished executing this routine, we ask it to give the control back to the caller. In the previous example, we saw that we read the entire port into register R0. In fact, we don't really have to read the entire port into the register. We can only work with specific data on the specific pins of the port. So microcontroller programming flexibility allows us to invoke the port bit specific addressing, in which we can address specific bits of some portion of the memory, including the memory mapped input output. So in this slide, we are going to discuss how input output port bit specific addressing is used to access selective data on the port. So this is a selective data IO operation technique. The first thing to note is that there is a concept of a base address of every port. So we are first going to take the base address of the port. In the previous example, we will first take the port address of the port A, the base address of the port A. And that address can be found from the data sheet, or perhaps it may be somewhere in the textbook as well, but I'm not sure about that. And then we add to the base address the offset. So two terms, the base and the offset. So the base address needs to be known, and then the offset. And then we're going to add we're going to add offset to the base. So base address is known a priori. What is not known, however, is the offset. For this purpose, we have a table. The table is very intuitive. The left column specifies the bit number, which corresponds to the pin number, and the right side corresponds to the offset that needs to be added. This table essentially says that if we wish to address bit 0 of any port, then the offset that needs to be added to the base address is hex 0004. For 1, it is hex 0008. 2, it is hex 10. And this goes on till we reach the last bit. That is, if we wish to access bit number 7 of the port, or the pin number 7 data, then add hex 0200. What's more interesting is that we can be selective in a way that we may be interested in a subset of bits. So for instance, if we are interested in reading data from pin number 1 and pin number 4, then there is a combined offset, that is hex 0040 and hex 0008. The sum of the two will be the offset that needs to be added to the base address. Let's take a look at an example. In order to address pin number 0 and pin number 4 of port F, they're usually designated as PF4 and PF0 respectively. And we are interested in selectively reading or writing data corresponding to these port pins. Then we're going to we are going to calculate the effective address as follows. So this is the address that we are going to obtain at the end of the day. But we need to look at first how to calculate this address. Well, the first component is the base address. This is the base address. That is the base address of port F. So port F has a base address that is hex 4002500. And then the next two are the offset. So remember, hex 0004 corresponds to the offset when we wish to access bit 0 or pin 0, and hex 0040 corresponds to the offset if we wish to access pin number 4 or bit number 4. And that the total turns out to be hex 400250044. Another example is that if we are just interested in addressing a single pin of port A, that is pin number 5, then we are going to add an offset. Again, this was taken from the table, hex 0080, to be added to the base address of port A, that is hex 4000400. The total is hex 4004080. And we're going to use this address to access pin number 5 on port A in our next program. This is another routine, switch input 2. We are once again interested in reading the status of the switch that is connected to port A pin number 5. But in this case, we are going to use the bit specific addressing. That is, we are going to we are not going to read in the entire data on the port. We are just going to access the data on pin number 5, or we are going to write data on just pin number 5 and leave the remaining bits or the pins on port A unchanged. With that in mind, we first need to define the address corresponding to the pin number 5 on port A. And as we saw in the previous slide, this address was calculated and it turned out to be hex 4004080. That needs to be stored as a constant. And that constant usually goes into the ROM. That's where the code is placed, the code that microcontroller is supposed to be run. To store this constant, we make use of the assembler directive, that is EQU. This command says that define a global constant. It's kind of a global constant, PA5. Define a constant value. So PA5 is going to hold a constant value. It is going to hold a constant value that is equal to the address of port A pin number 5. So for the rest of the program, we're going to refer to PA5, which is much easier than referring to the complete address, which is a bit cumbersome to write and read over and over again. So PA5 really means just this address. The first command is now loading the address of not the port A, but just the address of pin number 5 of port A. That goes into R1. Use indexing and read in the data of port A, pin number 5, and that data goes into R node. Now note that port A pin 5 is just one pin. It's a single pin. So when we load the data into the register, then the pin number 5 data uh, is going to go into the bit 5 of R naught. So bit 5 of R naught contains pin number 5 data, and all other bits of the register are set equals to 0. Therefore, if the switch has been pressed, again using the positive logic, we are going to use positive logic here again. So if that is a positive logic, then if the switch is pressed, then it is connected to high voltage, and then the port pin will be 1. So that means that we are going to read hex 20, the last 8 bits. So again, although these registers are 32 bits long, but here we are only mentioning the last 32 bits, last 8 bits. The last 8 bits hex 20. There's only one value that is at bit number 5 position. That's when the switch is pressed. And if the switch is not pressed, then the port is pulled down to the ground. It contains 0 at pin number 5. And all other bits of R naught are also 0. And then return to the caller. So this is another example in which we can just make use of the bit specific address to access the port pin instead of reading the entire data on the port. We are now going to describe how to interface a simple LED with a microcontroller. And I guess we are familiar with the ordinary diode, where the voltage drop is about 0.7. That's when the diode is turned on. The LED, however, is a bit different. It's a light emitting diode. So a typical characteristic, the VI characteristic, is that we often have a voltage drop that is in excess of 0.7. So in this example, we have about 2-volt voltage drop. That's when 10 milliamps current is flowing through the LED. Again, we can connect LED to the microcontroller to be controlled either by a positive logic interface or by the negative logic interface. In case of positive logic, the pin of the microcontroller needs to be high, it needs to be set high so that it allows it provides current that flows through the LED. So here the current is flowing from the microcontroller into the LED, 1 milliamps current. That's not too large. And in case of negative logic, we set the microcontroller pin to low voltage so that it is now sinking the current coming from the power supply and going through the LED, eventually entering the microcontroller. In both these examples, the current was small, 1 milliamps only. As long as the total current that microcontroller needs to provide or sink is less than it, in some cases 10 milliamps, but we have to look at the exact numbers in the data sheet. So within that range, microcontroller can safely drive an LED. That's the low current LED interface. When the current that is being driven out of that is supplied by the microcontroller, or the current that is that the microcontroller is sinking is small. The total current, if it is about 8 milliamps, this is the circuit that in principle should work fine, both in the positive and the negative logic. If, on the other hand, the LED current is in excess of 8 milliamps, such as in this example, the LED the current passing through the LED is 10 milliamps. Now, quite naturally, if we just allow this current directly to go and enter the microcontroller, it may actually be detrimental to the microcontroller. It may actually burn. In this case, we may be interested in inserting some kind of a buffer, such as ULN 2003B or 7407, 7406 or 5. But in this specific example, it is 7407. that can sink larger amount of current as compared to the microcontroller. So the current really enters the LED, and uh, it is consumed. It actually goes to the ground, passing through the buffer, and the microcontroller remains safe. However, microcontroller does need to provide an input to this buffer. So in this case, this buffer is working in a logic, specific logic, such that when the input is high, then the output is low. The 7407 IC produces a low output when the input is high, and it produces a high impedance state, that is Z, when the input is low. So when the input is low, there can be no current passing through the LED. But yes, if the input is high, then the output is low, meaning that the uh, LED can, there is some current that can pass through the LED. Or you can use ULN 2000B or some other appropriate buffer. So this is very important for the sake of the health of the microcontroller. You need to be able to determine the current requirement, how much current that the microcontroller needs to output, or how much current that the microcontroller may sink in. And if that is high, then do not forget to insert a buffer, again, in this case. Same goes if we want to use the LED in the positive logic. And accordingly, you have to calculate the values of resistances. So a lot of time, this part of this step is ignored, resulting in the malfunctioning of the microcontroller. So choose your resistance very carefully, and for that you need to be able to understand the current requirement of the microcontroller, and also the IC that is connected between the microcontroller and the LED. An example, a semi-language program that initializes uh, port E bit 0 to be interfaced with an LED. And remember, this can be easily switched to any other port pins as feel appropriate, but this is just a standalone example. Using the bit specific addressing, we use the assembler directive and define the address of port E bit 0. Port PE0 equals to hex 4005C004. And the first step is to enable the clock. For that, we set the clock register to hex 10. The upper 24 bits are all zeros. Then we wait for the clock to become stable. And once the clock becomes stable, then we proceed and then set the direction of port E bit 0. In this case, we want to make port E bit 0 as the output. So we take the OR of the register R0, that is containing the data of direction register, with hex 01. Once set as an output port, the final step would be to load the port E digital enable register bits in a way that the 0th pin of port E becomes a digital pin. So again, taking an OR of register R0 with hex 01 is going to set the first bit of R0 to 1, and when written back, it is going to update the port E direction enable register. So we have seen these steps many times before, but just for the sake of revision, these are reproduced once again. Now let us look at three different pieces of the codes. One of them is turning an LED off, the other one is turning LED on, and the third one is toggling the LED. That is, if the LED was previously on, it would turn it off, and vice versa. So suppose that LED is connected to bit 2 or pin 2 of port F. And if we are interested in accessing that port pin using the address turns out to be using the bit specific addressing, then the address turns out to be hex 4002510. It's been redefined over here. So repeating the same steps that we have seen so many times already, we are going to put the address, the bit specific address of port F pin number 2, and then we are going to move value 0 into register R0, right? So this move command simply copies this value that is in the second operand into the first operand. So R0 is 0. So because the entire register is 0, the bit 2 is also equal to 0. And then we are going to store this value to the memory location pointed to by the register R1. The R1 is actually pointing to the port F, pin number 2. So when this command is executed, it is only going to update pin number 2 of port F. So only PF2 will be equals to 0 only. So this only is very important here. The bit specific addressing allows us to only modify specific subsets of the bits on the port and then return to the caller. If, however, we wish to turn on the LED, we put the address of port F pin number 2 into register R1. We move the value, this time hex 04. That is, all of the bits of R0 are 0 except for bit number 1. Bit number 2. And then we write back that value to the port. And because we're using bit specific addressing, we only update the port F2 value, port F pin number 2 value only. Return to the caller. Toggle, the same program, except that we are going to use the exclusive OR on we're going to use the exclusive OR on pin number let me see, this is again, sorry, so this is pin number 2. This is a mistake here, so pin number 2, please make this correction. So take an exclusive OR of R0 with hex 04, which is going to toggle, which is only going to flip bit number 2 of R0. All of the bits remain unchanged, write back, and that is going to update the value on the logic value on bit number 2 port F. Return to the caller. Recall that in the previous lecture we briefly discussed the role of the code bits, and here we're going to discuss them in a bit more detail. There are 4 code bits: the negative, 0, overflow, and carry. So first look at the C bit. The carry bit is set equals to 1 after an unsigned addition, when the unsigned addition outputs a wrong answer, and it is 0 if the unsigned subtraction yields a wrong answer. The overflow bit is set equals to 1 after unsigned arithmetic, that is addition or subtraction, whenever the answer goes wrong. The Z bit is 1 whenever the result is 0. For our next program, we are specifically interested in the last code bit, that is the Z bit. If a result of addition or subtraction or some other arithmetic operation or logical operation is 0, then the Z bit is set equals to 1, and this can be used to make decisions and to execute programs conditionally. That is the concept of branching, analogous to the if-else statement in the high-level language. There is one bit that has not been described, that is the n bit. This is 1 whenever the result is negative. If at any point we need to use that negative bit in more, then I will describe its role in more detail. But for now, we're going to use the description of the z bit and write an assembly language program that conditionally executes some instructions. Our main routine in this assembly language program is the main that says branch and link to LED init. So we are going to first execute LED init routine, which we saw in the previous slide. And once that is finished, then we enter the part of the program beginning with the label loop. So loop is actually a label of this instruction, the move instruction, and the main was a label of the previous instruction. So we're going to move number 1. So essentially we're just going to set the least significant bit of r naught equals to 1. And then we execute a routine LED on. So we have seen samples of this routine before. So that assuming that the LED is connected to the least significant bit of some port, this routine will turn on the LED. The next instruction is essentially a preparation for introducing the delay. So once the LED is turned on, we want to remain it on for some period of time. So we are again going to use the value of register R0. So remember, when the last time value of register was updated, it was written to the IO ports inside the routine. And once we are back to executing our part of the main program over here, then we are going to reuse the value, this time a different value. This is the value that corresponds to the delay. The previous value was to turn on the LED. So that's why, in a sense, your program variables adequately map to the registers inside the microcontroller. This value actually corresponds to the amount of delay, as we shall see shortly. With the value R0 set equals to 25,000, that's decimal value, we call a routine known as the delay. Now let's go and look at the routine delay. The routine delay subtracts the value of register, and it subtracts, in fact, it decrements the value of register R0. And as long as the value is higher than 0, then we keep on executing this instruction. So if the initial value of R0 is 25,000, that is this value, we are going to keep repeating this instruction 25,000 times before moving on. Therefore, the microcontroller will be kind of stuck here, executing this instruction over and over and over and over again, as many as 25,000 times. And it is not going to do anything else, essentially, as far as our application is concerned. But how to make sure that the microcontroller jumps back to the same instruction over and over again? We introduce a command known as BNE, branch if not equal. So B for branch, N for not, E for equal. This is a conditional statement, or the conditional instruction. It says that you are going to go to the delay label. Now remember, the delay is actually the label of the routine. It actually corresponds to the label of an instruction, the first instruction of the routine. It says that go to the label, that is delay, if the 0 code bit is 1. If the 0 code bit is actually not equals to 1. So make a correction here, this is not equals to 1. So each time We execute this instruction, we come down over here, we check if the 0 bit is equal to 1 or not. We ask this question, and if it is not equals to 1, that is it is 0, then go back to execute the previous instruction whose label is delay. So keep on executing this instruction as long as the 0 flag is not equal to 1. Therefore, when the 0 flag is not equal to 1, we execute the first instruction. The moment 0 flag becomes equal to 1, then we do not go back to delay. In fact, we come down over here, essentially executing the return instruction, the final instruction on the routine. So how did we affect the value of the 0 flag is a missing link in our discussion. Essentially, this subtraction instruction is going to affect the value of the code bit. And we have specifically written sub s. Remember this suffix s. We are saying that we are asking our microcontroller to update the value of the code bits, including the 0 flag bit. It is going to be updated each time the subtraction is executed. And if the value of the subtraction is not 0, then the 0 flag remains 0. And whenever, so essentially, let me write it down over here. So z is equal to 0 as long as r naught is greater than 0. And the moment when r naught is equal to 0, z flag is set equals to 1. That's when you go to the next instruction. You don't go back to delay, you execute next instruction. That is return to the caller. So once that is done, we return to the instruction over here. Actually, we return to the next instruction over here, the instruction after this BL delay, because this instruction took the program counter to execute this routine. So once that's executed, we'll return to the instruction after the BL delay, and then now we are going to move the value r naught equals to 0. Okay, what is the purpose of this value? Setting r naught equals to 0 is going to turn off LED. With the intention is to turn off the LED. LED is not turned off yet until we actually write the value of r naught to the address of port to the IO port that we are using, and we have seen the code, example code of that before. So in this routine, if you go two slides back, the value of register is written to the port and the port data is updated. That will actually turn off the LED. Again, we are assuming that the LED is connected to some least significant pin of some port. So executing this LED off routine will turn off the LED. We are again going to reuse r naught. This time we initialize r naught with 25,000. That corresponds to the amount of delay. Execute the delay routine once again. So we are essentially going to wait for another 250,000 steps. I apologize, keep reading this value as 25,000. In fact, this is 250,000. So my controller is going to do nothing. It will just wait, essentially do nothing useful for 250,000 time steps required to execute this instruction, plus some overhead, and then that do nothing or wait time period adds to the delay, or constitutes the delay. And then once the LED remains off for this much time, the delay has finished, then we are going to go back to the loop. So this process repeats, and in the next cycle, the LED will be turned on, remain on for 250,000 time steps, and then LED is turned off, remain off for about 250,000 time steps. So this actually is going to generate a square wave on the port, some port pin, the least significant bit on some port, and essentially that is equivalent to toggling the LED with the toggle time delay, with the time delay corresponding to the 250,000 time steps. All right, so with that, I would like to conclude our lecture, except for the one last bit. That is about the homework. Do examples 4.1 to 4.3 from textbook number 1, the first textbook. That is your homework. And finally, I appreciate your patience watching this lecture. I hope you enjoyed this lecture and there was adequate learning stuff. We are going to have a follow-up Q&A session on Thursday afternoon starting at 2 p.m. Hopefully, we're going to have a longer Q&A session this time, covering the contents that we were unable to cover in the previous lecture. So do leave enough time after 3:30. We are going to have an extended Q&A this time, folks. And I would like to once again give slight credits to Jonathan Volvanos. His slides have been used and modified to fit the needs of our embedded system course. Thank you very much. Stay safe and have a nice day.